You're live. Sweet. What's going on, everyone? How are you tonight? I always find it funny that the people that don't watch this live and then they stream it later, they just see this. This is what they see. They see me sitting here talking to myself for a few minutes while people load up in the chat. We're just going to wait for one person to get in and verify everything's working okay. I see two people in the chat. Hello. Good evening. Happy Friday night. If you guys could just let me know if everything's cool. Audio's good. Video's good. It's working. Owen Chef, we have confirmation that it's working. Thank you very much. Hello from Buffalo. Oh, hi. We've got a hooray from Jackson and a what's up from Alexis. Hey, guys. Thanks for spending your Friday night with me. I'm going to get started right away so we have a nice packed 1 hour session of exciting review problems. Just going to pop over here. And we are going to put my iPad back on the screen. Okay, we are in business. Just going to pop back in the chat real quick. Hey, how's it going? Great, awesome, good stuff. It's not flipped for you guys, right? It always weirds me out that on my screen it's flipped. It's really strange. But we should be good. I think we're good. I'm going to get started, and if people yell at me that it's flipped in a second, I'll certainly revert and fix it for you guys. So hello, welcome to the not live review, which means it's the live review, obviously. For 3-1 and 3-2, let's get started. So just reviewing a couple of things real quickly. First of all, the definition of the derivative. The derivative of a function f with respect to the variable x is f prime, which is this thing right here. It's the limit as h goes to 0 of f of x plus h minus f of x over h, provided the limit exists. So this is our definition that we use constantly. And if you put an a instead in the function, so instead of x right here, just going to put it right here, and then you're evaluating the slope of the curve at a point. So this would be like if you plugged a into the derivative f prime x. That's what this formula would give you. I encourage you to use this formula when you only need to calculate the slope at one point. Like, for example, when we're doing our differentiability, and I only ask you to determine if there's a cusp, a vertical tangent, whatever, I would just do this at the questionable value. And it saves a lot of algebra headaches. It's not working. Oh, thanks, Jackson. Appreciate it. And then, of course, we have the alternate definition. And specifically at a point, x equals a. And it's just that the limit as x goes to a of f of x minus f of a over x minus a is equal to the derivative at a. And you can use this to calculate the general derivative if you just let a be the variable a. And then the resulting derivative is, of course, the general derivative of the function. Very important theorem in this section, that differentiability implies continuity. So if you know something is differentiable, then automatically you know the original function was continuous for all values of x. But it doesn't go backwards. So if you have continuity, that doesn't imply differentiability, right? We have to go through the appropriate tests. You could have a function that's completely continuous, like, for example, the absolute value of x. Completely continuous on its domain. However, that corner point is a point at x equals 0 where it is not differentiable. So just be cautious there and understand the theorem does not work backwards. Also, just make sure that f of x is continuous before you even consider differentiability. So if you're looking at a graph and I'm asking you questions about differentiability, if it's not continuous, then you don't even have to bother answering those questions. Okay? All right. Last thing I just decided to sneak in here, remember that the intermediate value theorem applies for derivatives. So if you have a function that's differentiable, meaning its derivative is continuous, then it takes on all values between f prime a and f prime b. So that problem we did with the circles and guaranteeing the existence of a 0 with a change from negative to positive or positive to negative, just be aware that this works for derivatives. So if I tell you an original function is differentiable, or if you could prove that to me, then you can, of course, say that the derivative must take on every value between f prime a and f prime b. So just be aware that that exists. Hi, Kaylee Furtado. Oh, Kaylee Furtado is an old student. Hi, thanks for joining the AP Calc Live Review, and nice to have you. Enjoy. I wonder if you're taking AP Calc or a calculus class in college, but let me know how you're doing. All right, so let's take a look at some problems. We were able to do this problem in 2 out of 3 of my classes, but my class with the fire drill today, we were unable to do this problem. So I wanted to do this tonight just to kind of kickstart things. I promised them that we would do it tonight during the live review. So let's get started. The idea behind this problem is I'm going to ask you to find values of a and b that make the function continuous and differentiable. Okay, so the first thing you'd want to do is always get rid of this absolute value here. In the absolute value itself, you always need to figure out which piece you're defined by, whether it's the positive side or the negative side, and then deal with it. So for example, if we know that f of x equals, if this is the absolute value of x minus 1, it's going to just be x minus 1 when x is less than 1, and actually this would be greater than 1, and negative x minus 1 when x is less than 1, and I'll just make this one equal to for the sake of having one of them equal to. So clearly I'm defined less than 1 in this problem, so I'm going to actually replace my absolute value of x minus 1. I'm going to replace that with a negative x minus 1. That's this piece right here being used for my absolute value. So I'm going to get rid of this now, and I'm going to rewrite my function f of x. So f of x, oh, hey, go away. So f of x is equal to, this is going to be negative x minus 1 plus 2, which is negative x plus 3 if x is less than 1. And the bottom piece remains unchanged if x is greater than or equal to 1. Okay, so now I have a function that I can actually go and start to prove, first of all, continuity, and second of all, differentiability. You remember I had you as a teacher freshman year. Yes, you did, Kaylee. It was great. And Flame says you're a multi-viewionaire. I really hope so, but I doubt it, seeing as how there's a whopping 8 viewers at the moment. But we'll see what happens. Okay, so let's see if we can figure this thing out now. Taking this function, the first thing you have to do is you have to show continuity. So let's do that first. So continuity basically means that the limit as x approaches 1 from the left of f of x equals the limit as x approaches 1 from the right of f of x. Okay, and then let's plug in our pieces. So left of 1, I'm negative x plus 3. And right of 1, I'm ax squared plus bx. So this is the limit as x goes to 1 from the right of ax squared plus bx. And this is the limit as x goes from 1 to the left of negative x plus 3. And now I can actually just solve this. I'm actually going to squeeze a page down here. Let's add a page. Okay, so this is equal to, if I plug a positive 1 right in here for a negative x, that's just going to be a negative 1 plus 3 is 2. And if I plug in a 1 here and a 1 here, I just get a plus b. So moving forward, in order for continuity to exist, the sum of a and b must equal 2. Okay? So now I think we're able to play the differentiability game. So if we now play the differentiability game, so differentiability will be over here. Actually, I'll just move it over a little bit. And you know, why don't we swap the color too? We don't want red. Why don't we do orange? Sweet. So in order for differentiability to be considered, continuity must be true. So we have to keep this in mind that a plus b needs to be 2. Now let's take our derivative, and then let's do the continuity test for our derivative, okay? So we'll put our derivative, I'm just going to squeeze it to the side of f of x real quick. I'm actually just going to shrink f of x and move it over. And we'll do an f prime x here. Now this would need to be done longhand with the definition. These are really simple polynomials, so I'm just going to use the shortcut for now. I have a couple of other definition of derivative questions in the slides here that are a little more complex, so I don't want to waste any time doing these ones out. Let's just use the shortcut. So the derivative of negative x plus 3 is negative 1 if x is less than 1, and the derivative of ax squared is 2ax to the first power, and then plus the derivative of bx is b, and that's if x is greater than or equal to 1. So in order for differentiability to be existing and to be clear, the limit as x goes from 1 to the left of f prime x needs to equal the limit as x goes to 1 from the right of f prime x. Okay, this is the continuity for the derivative, aka differentiability. So let's plug in our pieces here. So let's see, left of 1, we're at negative 1. And right of 1, we're at 2ax plus b. And let's squeeze the limits in. Limit as x goes 1 from the right. Okay, so let's go ahead and solve now. Plug in a 1 on the left side. There's nothing to plug it into. On the right side, there's one singular x, so it would be 2a plus b. So this is my second equation that must be true moving forward. So if both have to be true simultaneously, I can use a system of equations to create equality and find a and b together. So I'm just going to take my pink equation and just minus b both sides to say that a is equal to 2 minus b. And I'm going to use this substitution and put that value right into a right there, okay? So let's change to a nice red. Let's do negative 1 equals 2 times a, which is now 2 minus b plus b. So negative 1 is equal to 4 minus 2b plus b. So over here I've got, let's see, negative 2b and b make negative b. And if I minus 4, I'm going to get negative 5, giving me that b is positive 5. Okay, so here's value number 1. B is positive 5. And if I know b is positive 5, I know that a is equal to 2 minus b. So a is equal to 2 minus 5. So a is equal to negative 3. So I found my two values, a and b, that make this function continuous and differentiable. So that's a very typical continuity differentiability problem. The most important part of that problem is notation, right? So we talk about this all the time. You need to have either this line and this line. Okay, so those two lines are great, awesome. Then you can go plug and chug, do your math. Or you need to, I won't use orange, actually, I'll use like a green. Or you need to have this line and this green line right here. These two are perfect as well. Oh, wow, on my computer, they both look orange or yellow. Oh, on my iPad, they look green. That's okay. But you get the idea. You need to have either one of those limit notation expressions there. So just be aware that you need those. Let's check in the chat how we doing. Pogs? Pogs in the chat? I mean, I haven't done anything to deserve pogs yet. Let's just keep it going and see where things go. Okay, let's do some other problems. I've gathered just a bunch of random problems I'd like to take a look at. And this one is number 33. I think it was in section 3.1. If I'm wrong, it was in 3.2, because those are the only two sections that we're looking at tonight. So this one says, graph sine x and cosine x in the same viewing window. Which functions could be the derivative of the other? So kind of asking yourself, could cosine be the derivative of sine? Could sine be the derivative of cosine? Let's defend our answer using the graphs. Okay, so let's go ahead and graph these things. Let's just draw a nice little window here. Let's maybe just do pi and 2 pi. Let's do 1 period. Let's do sine x. Sine x will be in red, okay? So sine x, we know this goes down here and then returns up to here. And then we're going to just go like this and like that. Now it's a little bit, we'll just, oh, that's the whole curve. Cool. All right, we'll just try that again. And that's fine. Rough sketch is good. This is y equals sine x. And then we're going to do cosine x. Let's do it in pink. Let's do it in pink. And cosine x starts up here at 1. And then it's going to go all the way down, and it's going to return back up at 1. So we know we're going to kind of do one of these things like this. And I want to try to match up my values. That wasn't great. Let's try it again. So just try looking at the extrema here, trying to match it up nicely. It's just going to go, and we'll try that. All right, that's a little bit better. And this is y equals cosine x. Okay, so let's see if we can make a couple of arguments about the derivative. Let's first look at sine, okay? So let's keep our red as our original. So could the pink function be the derivative of the red function? Well, if we want to play derivative games, what we have to do is we have to first consider, what is the original function doing here? Well, the original function is increasing, right? Which means that the derivative should be positive. That's true. That's true. We have a positive derivative here. And then right here, and we'll kind of use a different color like a blue, right here we have a relative max. And what a relative maximum is of a function is a change from increasing to decreasing. What that needs to be as a derivative is an x-intercept, right? It's a change from positive to negative of the derivative. We do have that here, right? We have a change from a positive derivative to a negative derivative. And then we're going to do a lot of decreasing for a bit. We're going to do a lot of decreasing, and that means we're going to have a lot of negative derivative. This looks great so far. This looks great. And then right here, we're going to have a relative min, okay? And that's going to be a change of a decreasing to an increasing. which hopefully our derivative will change from negative to positive, which it totally does. And then we're going to return back here to this point. So it is clear, based on our normal differentiation rules, that the derivative of sine is cosine, because that derivative graph matches up perfectly. Let's make the argument the other way. All right, so let's erase these guys. Just erase this and this and this and this and this. Let's see if we can play the same game. Can I erase these highlights? Kind of. That's okay. Let's see if we can play the same game. So now we're going to pretend that the pink function is my original function, okay? So we're going to use like we'll just use a nice purple highlight. See if we can see that. So if my pink function is my original, I'm going to start up here. I'm going to decrease. I'm going to decrease. I'm going to decrease. I'm going to decrease, right? Which means my derivative had better be negative. It's not, right? It's not. It's positive. It's positive actually. And in fact, this whole region right here is all wrong. And then when we're supposed to switch, from a negative or decreasing to an increasing or increasing to decreasing right here at this value, our derivative actually does the opposite, right? When we're supposed to be negative and switch to positive, we're actually positive and switch to negative. So in fact, this function is the wrong sign all the time, which means that the derivative of cosine is actually negative sine. So if y equals sine x, y prime is cosine x. But if y is cosine x, y prime is negative sine x. And again, just kind of making that argument based on the general shapes of the graphs. Increasing means positive derivative, decreasing means negative derivative. Okay, check in with the chat. I'm a bit late, but I'm here. Hi, Ari, nice to see you. I gave Matt the concept quiz, or I gave him permission rather to send you a copy of it. But Ari, I also put it online, and anyone else who's watching, just chilling, I put the concept or the snap quiz right here. And I also actually put the topic outline that was on the back of the snap quiz. So these two documents are available on the planner if you're studying tonight or tomorrow or Sunday. Okay, coolness. Let's keep the fun going with some more problemos. Here we go. This is a function. This is number 10 in 3.2. It's asking when is the function continuous, when is it differentiable, and when is it continuous but not differentiable. So let's look at the graph. This is defined on negative 3 to 3. Is there any instance where this is not continuous? No, this is always continuous. Remember, what constitutes no continuity is a jump, vertical asymptote, a hole, or a what don't I have? Oscillating discontinuity, right? And none of that's true here. Continuity is if you had a pencil and you tried to trace your function, you could sketch the whole function without ever lifting your pencil. So that's the definition of continuity. So this thing is continuous, actually, for all values of x on its domain. So from negative 3 to 3. It's continuous forever. Cool. How about differentiability? Well, it is differentiable for most places, but this right here is an instantaneous change in slope. Right? So we are a positive slope, positive slope, positive slope, and all of a sudden now we're a negative slope. We're decreasing. And that's called a corner point, right? This is called a corner point. And likewise over here at x equals 2, this is another corner point. You need a gradual change of slope to be considered differentiable. Look down here at the base of this parabola. This is a nice representation of differentiability. It's nice and slow to slow down. It approaches 0. It then gets to 0. We have a horizontal tangent right there at x equals 0. And then we continue positively, starting slower and getting steeper as we go. That's nice differentiability right there. So x equals negative 2 and x equals 2, it's not differentiable. So differentiable, so we could say it's differentiable from negative 3 to negative 2. Union from 2 to, or actually it should be negative 2 to 2, union, and then we'll go from 2 to 3, and we'll bracket the 3 because we can. So differentiable basically everywhere on its domain except for negative 2 and positive 2. So just at those values, they need to be excluded from our differentiability. So where is it continuous but not differentiable? Well, it's continuous on its entire domain, and it's not differentiable at negative 2 and 2. So it's continuous but not differentiable when x is equal to negative 2 and when x is equal to 2. So at these two specific values, the function is continuous, but it's not differentiable. Okay. Yeah, so that's it. Check the chat. Chat's doing good. 9 people with me tonight. Wonderful. I know a lot of people had things to do, so they'll catch the video later, which is no problem. Let's try some more problems here. It's 8:50. We're doing good. Good pace so far. I just put a few here. Let's just do one at a time. Let's look at 40 first. Switch back to my yellow highlight. Number 40 says, if f has a derivative at x equals a, then f is continuous at x equals a. Justify, is this true or false? Okay, interesting. So it says f has a derivative. So what that means is that f is differentiable at a, right? Because that's what it has a derivative means, it's differentiable. It was differentiated and the derivative is there. So f is continuous? Absolutely. This is theorem number 1, right? This is theorem number 1. Sorry for my scrolling for a second. This theorem says that differentiability implies continuity. Okay, that's 100% true. If you have a function that has a derivative somewhere, then it's continuous right there. So let's go back to my question. And my question is going to be 100% true. And if I had to justify my answer, I would say that differentiability implies continuity. Differentiability implies continuity. Theorem number 1. Theorem number 1. Real quick question. I missed class today. So what is the format of the quiz? Is it going to be all no calc or what? It's going to be 2 parts. Sorry. So you're going to get a no calc piece first. That's going to take you most of the time, maybe about 40 minutes of the time. And then you'll have a little piece that's also calc active. And you'll get that after you turn in your first part. And then that'll take you maybe about 10 to 12 minutes to complete that part. So it'll be a little half and half mixture of those two. I'm pretty sure he said 4/5 no calc, 1/5 calc. Yeah, that sounds like something I'd say about 4/5 no calc, 1/5 calc. There's only a couple of calc questions, but you will definitely need your graphing calculators for this quiz. Don't forget your graphing calculators, okay? Some of these problems will be very hard without them. Okay, let's try another problem. Oh, go away. There you go. 41. 41 says, if f is continuous at x equals a, then f has a derivative at x equals a. Justify your answer. Well, this is the theorem that differentiability implies continuity in reverse. We already said this was false. Let's talk about why this is false. In order to justify something as false, really all you need is a counterexample, right? So let's just scooch this over here just for a moment, and I'm going to go ahead and create a counterexample. So I need something continuous at a and doesn't have a derivative at a. Well, I choose the absolute value of x, right? If f of x equals the absolute value of x, f of x is continuous at x equals 0, but not differentiable at x equals 0 due to a corner point. Okay, so that's a great counterexample to that claim. Absolute value of x is continuous for its entire domain, but it's not differentiable at 0. All right, so 41 is false. That's not true. 42. Okay, which of the following is true about the graph of x to the 4/5 power at 0? So this is a loaded question here. I want to do this out algebraically. I know you could do this graphically and probably get the answer relatively quickly, but I'd like to spend some time and do it algebraically. So I'm going to move this up. I'm actually just going to take these answers right out. I'm going to say bye-bye answers. And we're going to scooch this down. We've got a nice lot of room here. Let's see if we can solve this problem. So if I want to consider f of x to be x to the 4/5 power, what I really want to do is I want to take the derivative, and then I want to evaluate the left-hand derivative and the right-hand derivative, kind of see what's happening at my questionable value. So my questionable value in this case is 0. And the reason why is because I have to take my function, and I have to kind of take everything away from it, look at just the base of the function, and say what would make that base 0, what would kind of make that go to 0. And in this case, it's just a 0. So really what I want to do is I want to consider x equals 0. What happens when x equals 0? That's the question. In order to do this, I'm going to take my derivative, the limit, as h goes to 0, but I'm not going to calculate the general derivative. I don't care what the derivative is. I care about the derivative, the slope, exactly at 0. So I'm going to calculate the derivative at f of 0 plus h minus f of 0 all divide h. So this is calculating the slope at 0, and then I'm going to consider the left-hand side as 0 and the right-hand side as 0. Just a note, it's just a coincidence in this case that the limit of h is going to 0 and I'm plugging in 0. That doesn't have to happen. This value of f that I'm plugging in here into this f plus h and f of x thing, that can be any value of x that I'm questioning. Whereas this limit right here as h goes to 0 always has to go to 0. Your definition of the derivative is always h goes to 0. So don't ever change that, okay? So let's see if we can solve this. Let's add a page, and let's see if we can go. So limit equals limit as h goes to 0. All right, so this is going to be 0 plus h raised to the, what was it, 4, 5? Yeah, 4/5 power minus 0 to the 4/5 power all over h. Okay, and this is just equal to the limit as h goes to 0 of h to the 4/5 over h, because this goes to 0, and then this guy doesn't do anything. And so this is 5/5 on the bottom, right? So this is the limit as h goes to 0 of 1 over h to the 1/5. If I subtract 4/5 from the top and the bottom, I'm left with 0 on the top and 1/5 left on the bottom. So I could re-simplify this as the limit as h goes to 0 of 1 over, so if you guys remember from Algebra 2, this is the power and this is the root. Power, root. I taught my Algebra 2 kids that it's like Power Rangers. That's how I remember. Power Rangers, power root. I don't know, just something silly to help. So this is the 5th root of h to the 1st power. This is the question I'm asking. Okay, so what I want to consider is what's happening to the left and what's happening to the right. So in order to do that, I need to break this problem off into 2 separate problems. The first problem is the limit as h goes to 0 from the left of 1 over the 5th root of h to the 1st, and the limit as h goes to 0 from the right of 1 over the 5th root of h to the 1st. Okay, and let's see if we can evaluate these things. If I take a real tiny negative number, so I'm really, really close to 0 from the left side, so that's a very tiny negative, and I plug a very tiny negative in here, my very tiny negative gets 5th rooted, and it's raised to the 1st power, so it's still negative. And then I do 1 divided by a really tiny, tiny negative. This is 1 divided by a tiny negative number, and that's going to blow up and give me negative infinity. Because 1 divided by a tiny number gives me a really big number, and the denominator is still negative, and the numerator is positive, so that's going to be negative infinity. And over here, I'm going to plug in a real tiny positive going in here, raised to the 1st power, still positive, 5th root, still positive, but now it's even tinier. And 1 divided by a tiny positive number is going to be a really big positive number, okay? This is evidence of a cusp at x equals 0, because the limit from the left and the limit from the right are going to opposing infinities, okay? So we would say that f of x is not differentiable at x equals 0 since there exists a cusp there, okay? Just to review, when they're negative infinity and positive infinity from either side, so that's like both infinities, it's a cusp. If they were both signs were positive infinity or both signs were negative infinity, it'd be a vertical tangent. And then if they are approaching different constant values, like one approaches 5 and one approaches 6 from the left and the right, then you have a corner point because it's kind of like linear slopes there. Yeah, so that's an example there. You have a cusp. So I'm going to scroll back up real quick to the question. The question asked what type of non-differentiability was it? It was a cusp. It was letter B. All right, check in with the chat. How's the chat doing? I was never allowed to watch Power Rangers. I'm sorry, Nick. Power Rangers is so good. Love that acronym XD. I chose not to watch Power Rangers. Oh, that's no good. No Power Rangers. No SpongeBob either. Oh, now that's rough. That's just not good. Yeah, SpongeBob's great. SpongeBob, I attribute a lot of my creativity to SpongeBob and Calvin and Hobbes. SpongeBob and Calvin and Hobbes. Okay, let's keep the fun going. It is currently 8:59, which is nice. I got a few more problems prepared, and I'll turn it over to you guys for any Q&A, and then we'll call it a night. Let's try this one. It says, given the function f of x equals x squared plus x, let's find the slope of the curve using the definition of the derivative. Let's then find the equation of a tangent at -1 and a normal at 2. Let's do this. So first of all, let's go ahead and use our definition of the derivative. So this is going to be the limit as h goes to 0 of f of x plus h minus f of x all over h. And this, in this case, is going to be the limit as h goes to 0 of x plus h squared plus x plus h, because that's, ironically, that's going to be an x plus h, minus x squared plus x, we'll just do for now, over h. Okay, it's clear I'm going to need a lot more room, so I'm just going to add a page, and I'm just going to take this and go solve it on a separate sheet for a moment. And we'll go ahead and pick this party up right here. So equals the limit as h goes to 0 of x squared plus 2xh plus h squared plus h minus x squared minus x, making sure I did not forget to distribute this negative properly. It's very important, okay? So let's see what happens. X squared and negative x squared, positive x and negative x go away. So I am left with the limit as h goes to 0 of 2xh plus h squared plus h all over h. And I can now factor an h out. I can factor an h out. So this is going to be 2x plus h plus 1 over h. H is canceled. See you later. Lim as h goes to 0. That was a weird h. I was going to do an x for a minute there. We're just going to plug the h as 0 right in here. See you later. And this equals 2x plus 1, which if I go back and I use the shortcut really quickly, the original function is x squared plus x. So I know the derivative f prime x is 2x plus 1. So we're good. We're happy that definition worked. So I'm just going to get rid of it. See you later, definition of the derivative. And we're going to move this right there. Okay, so we did our definition of the derivative out, and we have our derivative. Now we need to find the tangent at x equals -1, okay? So the tangent at x equals -1, I need two things. I need a coordinate point, -1 comma something, and I need the slope f prime evaluated at -1. So I need to find these things. So let's go ahead and find the value first. So if I plug -1 into my original function in here, right? So I'll do it up here. We'll do it not in pink. We'll do it in red. F of 1 equals -1, not into a derivative, into the original, is equal to -1 squared minus 1, which is equal to 0. So this is a 0. So that's nice. And then I'm going to plug -1 into the derivative, and I'll do that up here. F prime of -1 is equal to 2 times -1 plus 1, which 2 times -1 is -2 plus 1 is -1. So I've got my point, I've got my slope, I've got my answer. We'll do it in orange. Y minus y1 equals the slope m, x minus x1. And this is my tangent. You can get rid of the 0 if you want, it doesn't matter. Let's do a normal. Normal this time, we're going to do it at x equals 2, okay? Now you play the same game. You do everything the same as a tangent. So you need to do, we'll use nice purple, my favorite color. So you need to find a point, 2 comma blank, and you need to plug 2 into the derivative. Okay, and let's go ahead and do these two things. So I'm going to do them over here this time. So f of 2 is 2 squared plus 2. 2 squared is 4 plus 2 makes 6. So that's my y value of my point. I plugged 2 into the original. Okay, even though this is a normal, I'm doing everything the same. All right. Now, 2 goes in the derivative, and 2 goes in the derivative, so it would be 2 times 2 plus 1. And this is going to be 4 plus 1, which is 5. So that's my slope. But that's my slope of my tangent. This is the slope of the tangent. So to find the slope of the normal is the opposite reciprocal slope, right? So -1/5. That's the only change with a normal or a tangent. No difference otherwise. So I'm going to just finish this up. Y minus y1 equals m, which is the slope, parentheses x minus x1, and there's my equation of my normal. Okay? The only weird thing I can throw at you is if I ask you for like horizontal tangents, which is just when the slope is 0, just set the derivative equal to 0. I could also make that function f of x super crazy nasty function and give you a graphing calculator, right? So real quickly, I can show you. Yeah, let's do that. Real quickly, if I just show you guys, what if I gave you some nasty function like the square root of 25x squared divided by the polynomial x to the 7th plus 3. Sure. This right here, if I asked you to find the slope of the tangent, you have to do a couple of things. First of all, you'd have to find the point. So if I go to the table here, let's say I asked you to do it at 1, just because it's the only value that's not insanely small. It'd be 1.25, so that'd be the y value. And then if I wanted to find the slope, I'd have to go to math, derivative, which is 8, x, and I click vars, go over to y vars, function y1, and press the right arrow, calculate the slope at 1. And I get my slope, which is negative 0.937 approximately. And so that's how you would do it if I gave you a function you weren't able to do on the without a calculator. All right, so really the same process, but the calculator kind of takes away some of the math for you if it's a crazy weird function. Check in the chat. Calvin and Hobbes for the win. Oh, absolutely. Calvin and Hobbes is great. All right, let's keep going. We've got some time left. I wanted to do one with the alternate definition because we haven't done one in quite a while. So I just wanted to get some exposure to that. Let's try this one. Let's say I wanted to find the derivative of 1 over x at 2 using the alternate definition, okay? So in this case, I'm going to do the limit as x approaches 2, a is going to be 2 here, okay, of 1 over x minus 1 over 2, all divided by x minus 2. Okay, and I'm asking you to solve for this. Now keep in mind, if we plugged in a value, this should come out to a numeric answer. I'm not finding a general derivative here. I'm finding the slope at 2, okay? So I'm going to go ahead and simplify. So the limit as x goes to 2. Now the numerator, I'm thinking we probably should get a common denominator. Common denominator here is going to be just product of the denominators. So what if I multiply this guy by a 2 over 2 and this guy by x over x? So let's see how this simplifies. So this would be 2 over 2x minus x over 2x. And I'm going to swing this up here times 1 over x minus 2. So that's the division of x minus 2 is multiplication of 1 over x minus 2. That just makes me happier. Let's see if we could combine the numerators. Lim as x goes to 2 of 2 minus x over 2x times 1 over x minus 2. I'm really close, but it looks like I probably need to factor a negative 1 out of the numerator so I can get those factors to cancel. So if I rearrange these terms and pull out a negative, it would be negative 1 or negative, and it'd be x minus 2, right? Did I do that right? Because if I rewrite these, this is negative x plus 2, like right here. So I want it to be pull the negative out so I cancel. So it's gonna want that times 1 over x minus 2, and then they just piece each other out. I do have the negative on top though, so don't forget about that. So this is going to equal the limit as x goes to 2 of negative 1 over 2x, which I can now just do a direct substitution to get negative 1 over 4. Okay, so I can do a direct substitution there to get negative 1 over 4. It's worthwhile showing you just really briefly, if I wanted to do this with the shortcut. So 1 over x is really just x to the negative first power. So its derivative, you bring the constant down, the exponent comes down, so negative 1x, and you reduce the power by 1. So minus 1 from negative 1, you get negative 2. So then this derivative is actually just negative 1 over x to the positive 2, right? So if I plug a 2 into that, you get negative 1 over 4, which is exactly what we just got using the alternate definition. All right, so just wanted to do one for fun. Chat is happy, so we're going to keep going. Look at this guy. The graph of the function is shown here, made of line segments joined end to end. Graph the function's derivative. At what values is it not differentiable? All right, let's try the derivative here. Now, typically, the derivative is just a rough sketching, right? That's all I want from you guys, just a rough sketch. This one's weird, though, because all of these are linear. And so the derivative of any linear function is actually just a constant, right? So I feel when it's just linears, we have to be a little bit more meticulous. We have to find the actual constant. And you may think, well, how do we do that? Well, you just find the slope, right? The slope of this line segment is y2 minus y1 over x2 minus x1, which is -2 over -4, which is +1/2. So the slope here is +1/2. So I'm just going to put that right here. And we'll leave that there for a minute. Let's just do all of them real quick, and then we'll go and draw it. So let's do this one next. So the slope of that one is y2 minus y1 over x2 minus x1. And that's 4 over 1, which is 4. So the slope is 4. I should be negative, though. What did I do wrong? 2 minus a -2 is 2 plus 2. And then 0 minus 1. That's what I did wrong. I swapped the order of these. 0 minus 1 should be -1. So -4 would be the slope of this one. I know that seemed off because it's sloping downwards. So I should get a negative there. This one's easy. It's just 0. Slope of any horizontal line is 0. And then this one I could do as well. So the slope is equal to, let's do y2 minus y1 over x2 minus x1. And this is going to be 2 over 2 is 0. Oh, let's see. That's definitely not right. Oh, it's 4. 4 over 2, which is 2. And that's supposed to be a positive slope. So we're okay there. So now that I've got all my slopes calculated, I can just go ahead and do a quick sketching of the graph, all right? So I'm going to do this in, blue's too close to the original. We'll just do it in black. So from -4 to 0, the derivative is 1/2. So that's like right here. And over to right here. Okay, so that's from -4 to 0. It's 1/2. Then from 0 to 1, it's -4, which is down here. So it's like right here. So right there. And then it's going to be 0 from 1 to 4. From 1 to 4, it's going to be 0. It's going to be 0. And then from 4 to 6, it's going to be 2. +1, +2 right here. +2 right there. Okay. And you may ask yourself, Mr. Schachter, should we put open circles, closed circles, one of each? Well, interestingly enough, each one of these points that we looked at is actually a change of slope, right? So each one of those points where we kind of jump, the derivative is not defined, right? So the derivative is not defined there at 0, 2. So I'm actually just going to make sure I use an open circle here and here because I don't have a value of the derivative there, okay? The same thing's going to happen here. I'm going to make sure I have open circles here. I'm going to make sure I have open circles here. And I think I got them also 1, 2, 3. Wonderful. Ironically, by having that conversation, we just kind of answered B, which is at what values is it not differentiable? Well, it's not differentiable wherever the derivative is not defined. And specifically, it's not differentiable wherever the slope changes too rapidly or you have a corner point. So that's going to occur at 0, x equals 0, there's a corner point. At x equals 1, there's a corner point. And at x equals 4, there's a corner point. Just make sure I didn't miss any of them. So this is good. This is 0. And then that's okay up until 1. That's not okay. And then 4, that's not okay as well. And I think we got them all. So that's just a fun and exciting problem. Looks like the Big Dipper. Does it? I don't really know constellations that well, but I'll take your word for it, Jackson. All right, we're moving on. It is 9:14. We've got some time left. So this is the last problem I have in the notes. It's just another continuity differentiability problem. I figured we could run through it if you'd like, but we've only got 15 minutes, so I definitely wanted to open up for Q&A. So I'll kind of wait and see if there's any questions in the chat. And if there are not any questions in the chat, we can do 44. Or if someone just says, let's do 44, then we can do 44 as well. So just let me know what you guys would like to focus on. How do you not know the Big Dipper? I just don't, Nick. I just don't. Yeah. So, I would love to see 44. Can we learn about the Big Dipper? Yeah, just open up a new tab and just Google the Big Dipper, and then bam. And we got another vote for 44, so let's do 44. Okay, find the unique value of k that makes the function differentiable at x equals 1. I'm going to get some water real quick. So this looks actually quite easy. There's only 2 variables. So the ones we've been doing in class have had 3 variables, so they've been a little harder. All right, let's do this one legit too. Let's not do any shortcuts. Let's do the whole shebang. Find k that makes this differentiable. Okay, so you get that? Okay. Step one is always continuity. Continuity. So continuity states that the limit as x approaches, now what's my value? I got to do 1 here. As x approaches 1 from the left of f of x equals the limit as x approaches 1 from the right of f of x. Okay, so let's go ahead and plug these in. So this is the limit as x goes to 1 from the left of 1, I'm x cubed, and then the right of 1 is 3x plus k. All right, so let's go ahead and find this. So if I plug a 1 in here, I get 1 cubed is 1. If I plug a 1 in here, I get 3 times 1 is 3 plus k, and I get k is negative 2. Oh. All right. So that's it. I guess I don't have to do anything else because I don't have to consider a derivative, because if k is anything other than negative 2, this thing's not continuous. All right, well, that was too easy. But you know what I guess we could do is maybe we could just take the derivative for fun and verify it's continuous at negative 2, because I guess maybe we couldn't assume that right now. We don't know if it's going to be differentiable. Yeah, I mean, why don't we do that? Because I guess you wouldn't be able to say 100% that it's continuous at if that's negative 2. I mean, I guess you would, though, because that's the only thing that could make f of x continuous, and you need continuity for, differentiability. So I don't know. Let's just practice my definition of my derivative, though, because we have this problem in here. Okay, so let's go ahead. You know what? Let's new page it. New page it. Let's grab my function. Did you new page it? Thank you. Grab my function, copy, and let's paste it. Okay. Oh, that's cool. Copied. Not what I wanted to copy. All right, go away. And now let's copy it. Oh, there it goes. And we're pasting. All right, that's cool. So, oh, yeah. So let's find my derivative. So f prime x is going to equal, so let's cheat first and let's do the definition after. So let's cheat first. This is 2x squared. If x is less than or equal to 1, oops, my bad, 3x squared. And then the derivative of 3x is 3. And the derivative of k with respect to x is 0, because k is a constant. So greater than 1. Okay, so now let's go ahead and find them out longhand. So the limit as h approaches 0 of x plus h cubed minus x cubed over h. So we're going to find the derivative of the top piece here. So this is equal to the limit as h goes to 0 of x plus h times, I'm going to multiply 2 of them together. I feel like I'm having deja vu from class today. X squared plus 2xh plus h squared minus x cubed over h is equal to the limit as h approaches 0. Now I'm going to distribute an x into everything. Okay, so this is equal to x cubed plus 2x squared h plus xh squared, and then I'm going to distribute an h into everything, okay? So this is now equal to plus x squared h plus 2xh squared plus h cubed minus x cubed over h, okay? Let's see what cancels for me here. Negative x cubed and x cubed, gone, and nothing else. So why don't we do the limit as h goes to 0 of, let's pull an h out of everybody. So h, parenthesis, 2x squared plus xh plus x squared plus 2xh plus h squared over h. H's cancel. And then I'm going to plug my 0 right in here for h. So this guy makes this go away. This makes this go away. And this goes away. So I'm left with the limit. No more limit. I just plugged my limit in. So I'm left with 2x squared plus x squared, which is 3x squared. So my derivative 3x squared confirmed using the definition of the top piece there. Okay, and then let's just do the other one as well, just to get some practice. I'll probably need a fresh page. Ooh, I've already got a fresh page. So the other one is 3x plus k. So if f of x is 3x plus k, then the limit as h goes to 0 of 3 times x plus h plus k minus 3x plus k in parentheses all over h. So this equals the limit as h goes to 0 of 3x squared plus, so it'd be 2xh, so it'd be 6xh plus 3h squared plus k minus 3x minus k over h. I just, I expanded this thing. Oh, wait, I just squared that for no reason. Oh, I'm on autopilot. I just keep squaring the binomial x plus h so many times. It's just distribution of 3. 3x plus 3h plus k minus 3x minus k. All right, that's a little better. Gone, 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 gone. And I'm going to get limit as h goes to 0 of 3h over h, which is boom, boom, 3. And there's no x's left, or h's rather, to plug in that 0. So that the derivative is 3. So I've confirmed both derivatives. So now I can officially work with my derivative. And my derivative basically just states that the limit from the left has to equal the limit from the right as x equals 1. But as you can see, if I went and I did that, look at what happened. If I plug the 1 in the left-hand derivative and a 1 in the right-hand derivative, I would just have 3 equals 3, which would basically be stating that this derivative is totally fine at 1. There's no discontinuities there. As long as k is equal to -2, that there's no discontinuities there. So that one was a bit too easy, but it was some good definition practice. Let's check in on the chat. Let's go back. I'd love to see 44. Can we learn what Big Dipper is? Let's see that 44. There's the Big Dipper. Oops, it didn't work. Have to use the bit.ly before law. Cool. All right. Is there any other questions or concerns before we close the live review? Anything you guys are worried about? I guess for the last couple seconds, I can also just pull up the topic list real quick. Where's my mouse? There you are, mouse. Topic outline. And here you are. So this is kind of us. This is our assessment tomorrow. So we're kind of looking at the definition of the derivative. Oh, I got to pull my chat up. There's my chat. Can we see a problem like this one? Which one? We see another problem like this one. Oh, another one just like 44, like a continuity differentiability problem, like that one, James Bugoli. Are you a student of mine? I'm pretty good with names, but I don't know if I know you. James. Yes. Is that your name, James Bugoli? This is going to be really awkward on Monday if I'm actually having a conversation with you and that's your name. So I do apologize. And what period are you in, James? James. I'm Jackson. Oh, you're Jackson's from Buffalo. Yes, he was talking to me about you today. That's fantastic. Hi, how are you? Yeah, James, we've done a bunch in class already. Let me pull one up for you. I think this was one that we did on our snap quiz. So James, a snap quiz for us is like I'm just trying to, trying to pull my chat back up. There's my chat, and I'm gonna get that snap quiz back up for you. There you go. So this one is another one we did, number 3, and it's kind of using the same idea of continuity differentiability. And number 3 works out to be a little bit more friendly as well. You don't need a system of equations like the one I did in the beginning of the video. So it's kind of neat. I would definitely recommend trying it. Just real quickly, if I remember from class, I think A was supposed to equal, what was it, like -1/3 or something, and B was, positive 1/3, positive 1/3. Anyone have the answer written down? I want to give it to James before I cancel the stream. I mean, we can do it, I guess. Here, let's do it real quick. I'm going to take a picture of this. And we're going to snip it. All right, why don't we just end the review with this problem, because it's a good problem anyways. I'm going to pull the iPad. I just wanted to snip that problem and bring it back up. And, oh, there we go. Nick has the answer for us right there. So, okay. And we've got, oh, I need my problem back. Come back, problem. Come back to me. So, f of x was equal to ax cubed when x is less than 2, and x squared plus b when x is greater than or equal to 2. So I won't do out the definition this time just to make things go a bit quicker. I'm just going to pull my chat back up. Here we go. But we can do out the continuity and the differentiability pieces. So for continuity, the limit as x approaches 2 from the left of f of x needs to equal the limit as x approaches 2 from the right of f of x. And so if I plug in my pieces now, this is the limit as x approaches 2 from the left of ax cubed, and the limit as x approaches 2 from the right of x squared plus b. So now I can just plug a 2 in, So this is 8a equals 4 plus b. So this statement must be true. Like I mentioned, I'm going to just cheat and use the definition, or not use the definition real quick. Here, we'll just shrink you, move you over. And the derivative f prime x will equal, so with respect to x, the derivative of ax cubed is 3ax to the second power, 3ax squared, and 2x, and then plus b, the derivative, it just goes away, and that's it. So let's go ahead now and use my differentiability piece. I'll use orange again. I'm liking the orange today. Differentiability piece. Limit as x goes to 2 from the left of f prime x equals the limit as x goes to 2 from the right of f prime x. Okay, so this is now my differentiability, which is just continuity on the derivative. So this is the limit as x goes to 2 from the left of 3ax squared, the limit as x goes to 2 from the right of 2x. And I think this is just going to equal, if I plug a 2 in and a 2 in, this is going to be 2 squared is 4 times 3 is 12a equals 2 times 2 is 4. Divide by 12, divide by 12, a is 4/12, which is 1/3. So if a is 1/3, I'm going to go back over here and plug it in. So then 8/3 equals 4 plus b minus 4 minus 4. So 8/3 minus 4, which is 12/3, is b. So b is negative 4/3. B is negative 4/3. Okay. So here's my a and my b. And that one you needed to carry out further to get continuity and differentiability to kind of work together. All right. And the chat, we got interstate. That's so exciting. That's awesome. Someday, interstate, intercountry, interworld. I'll be teaching AP calculus to other people on different planets. It'll be cool. I'll be ready. I hope you remember me when I'm that famous. Isn't b negative 4/3? Yeah, we did that, right? We got negative 4/3. Thanks, Matt. Was doing the dishes. My bad. It's negative 4/3. Yeah, we're all set. Thanks. That helped. I'll be back again next week. Awesome. Nice to have you, James. And thank you, everyone else, for tuning in. It's 9:28, so I'm going to sign off. I hope you guys have a wonderful day, and you can message me on Remind or send me an email if you have any other questions or concerns, okay? All right. Have a good Friday. Have a good weekend.